Hi, my name's Dan, and this video is one of a series of videos I'm doing about logic gates for digital electronics. And having previously in the series explained the 8 different logic gates, the standard set that are available, I just wanted to cap this off with a video about a thing called equivalency. In order to understand this, you need to know what these gates are and what they do. So watch the rest of my series first. And then watch this at the end. And this is kind of leading into the next short series that I'm going to do, which is about how to combine gates to make digital circuits of increasing complexity. But you can see here we've got 4 little circuits. We've got a circuit here with an XNOR gate in. The next one down is a circuit with an XOR gate and a NOT gate. This third one here has 5 NAND gates in it, combined in a specific way. And this last one here has got 4 NOR gates in it, combined also in a specific way. And the simulation is active and up and running, so all these circuits are running. And I want to demonstrate something and then talk about it, which is that these circuits, the process that happens between the input and the output is exactly the same, and it's the XNOR process. So we can see, if you watch the previous videos of this one, you'll see the XNOR gate. The output is high if both inputs are low, or if both inputs are high. But if they're not the same, then the output goes to 0. So that's the basic gate. When I did that video, I talked about it being the same as an XOR process followed by a NOT to NOT the output. And in fact, you can do that just by getting an XOR gate and a NOT gate. And we'll show that this is equivalence by flicking these inputs there. This next one is harder to work out because it's got several gates going on. I'm not going to track through and explain the wherewithals of exactly why, but I'm going to demonstrate that it is the same by doing the inputs in the same order and showing what's happening. And similarly, the bottom one, it's got the same output as inputs. Okay. And the thing that I want to demonstrate with this is that in digital electronics, there is always more than one way of achieving the same input to output combination. There is often a simplest way of doing it, given the gates that you've got. So the one at the top here is the simplest version. But for practical reasons, you might have other things that you want to do. And the next series that I'm going to do is talking about combining gates together to make circuits. And part of that will be talking about how you go about reducing the number of gates that you might be using. But sometimes you want to go the other way around and you want to increase the number of gates you're using for practical electronic reasons, because there is an interesting quality for both the NAND gates and the NOR gates, which is they're called universal gates, in that you can make any of the other gates out of a combination of one particular gate here. So this third circuit here, you can see an XNOR has been made out of using 5 NAND gates. And at the bottom, you can see an XNOR has been made by using 4 NOR gates. Any of the 8 gates can be made out of an equivalent circuit from just NAND gates and NOR gates. And the good news with that for practical electronics is that this means that if you wanted to do some fairly simple digital electronics and you didn't know which gates you were going to use, you could just buy a whole load of chips that have NAND gates on them or a whole load of chips with NOR gates on them, and you could produce any circuit that you wanted out of that as long as you'd got enough, because you can create the equivalency of the other gates. So that's just a quick explanation of this idea that it's possible for 2 circuits to have the same effect and can be equivalent, and for the fact that the NAND gates and the NOR gates are special in that they're universal gates and you can produce any of the gates from combinations of them. That is it from me for now.